Again, if you have a question, throw it up in the chat or unmute your mic and go ahead and ask it. What we're going to start with today is looking at benchmarking benzene and monosubstituted benzenes relative to that, so that we can start looking at the synthesis of higher order benzene molecules. So we're continuing our education of aromatic chemistry here. And what I want to do sort of in this upper area here is write benzene in the middle. So benzene is going to be our benchmark. And what we are doing, we're going to write a bunch of compounds over here to the right that are going to be more activated than benzene. So these are electron donating substituents. Then to the left, we're going to write a bunch of benzene molecules that are deactivated. So they're going to have electron withdrawing groups. And so we want to talk about the nature of those substituents relative to benzene, how they're going to direct a second reaction, and the rate at which they do so. So this might get a little tight here, so I'm going to draw them fairly close together. So again, benzene is our benchmark rate. Everything over to this side will react faster than benzene itself. So we have just a simple methyl group. So we have toluene. So now we have an ester where the oxygen of the ester is attached to the benzene. Next, we're going to have an amide. So an amide where the amide nitrogen is attached to the benzene. Then we have phenol. And I sort of ran out of room, but I'm going to write it over here under it. We have aniline. So all of these molecules here we're going to say that the benzene ring itself is activated relative to the just regular benzene by itself. So these substituents are all pushing electron density into the ring. So we're going to say these are electron donating groups. The methyl case here is the only one that does not have lone pairs of electrons. And so what this does, it activates through induction. And that's through the bond. The rest of these all do it through the lone pairs of electrons in resonance. So the lone pairs resonate into the ring. It makes the ring more electron rich than benzene itself. So these are electron donating groups. So to the left here, I'm going to draw a bunch of different benzenes as well. The first one we'll start off with is chlorobenzene. This one is sort of an oddball in that the ring is activated, but the substituent itself is categorized as electron withdrawn. So I'll make that distinction after we write the rest of these up. So all of these are going to have substituents essentially that have a double bond next to the benzene ring. So we have a nitrile C triple bond N. So that's electron withdrawing. Next, we're going to have anything with a carbonyl. So this can be aldehyde, ketone, acid, ester, amide. So note the difference here. The carbonyl is bonded directly to the ring, whereas over here in this ester and this amide, you have the heteroatom and then the carbonyl. So note the difference here, CF3 versus CH3. This pulls electron density the other way. And then the last one, which I'll draw below, since I ran out of room, is the nitro group. And again, these are substituents that deactivate the ring, so we're going to call them electron withdrawing groups. So I'm underlining these terms because those are what we're going to need to really know moving forward in the next 3 lectures here. So I said that the chlorobenzene was sort of the oddball, and because I can extend this line, the lone pairs can donate into the ring and activate, which they do, but by electronegativity, we think of induction. There's some overlap here, but we're going to classify the halogens as electron donating groups. And that's what's going to be important for us moving forward in these next couple slides here. Before I move on, any questions so far? So maybe let me recap this. The point of looking at these structures, unsubstituted benzene, all the substituents are H. That is our benchmark of 1 if we're talking about a rate. These substituents shown here to the right all activate the benzene ring so that they'll react faster than 1. We don't have exact numbers we can put down here. We can just say in a race between this and this will react faster than benzene. On this side, these substituents all deactivate the benzene ring. So if you have one of these will react slower than benzene. And we'll see why that's important if you have a molecule that has 2 benzene rings in it, 2 different benzene rings in one molecule. You can look at the substituents and say, okay, if this was present and this one was present, and you were treating with one equivalent of an electrophile, this one would react first over that one. So that's going to be important for us. The second thing that's important for us is understanding with this existing substituent on there, where does the next electrophile go? So maybe in this space right here, I can show you the general rule that we're going to follow for this. So electron donating groups that you see, they will direct the second substitution to the ortho and para positions. So ortho, para. Electron withdrawing groups direct a second substitution to meta. So if we're looking at starting with any one of these and doing a second reaction on the benzene ring, we first categorize what type of substituent it is: electron donating, electron withdrawing. If it's this, it's going to direct either ortho or para. Para is typically preferred to ortho due to steric reasons. If the existing substituent is electron withdrawing, the second one's going to go meta. Any questions on that? I'm going to go ahead and erase this board. We'll put up a problem to see this logic in action. So while I'm erasing here, I forgot to activate quiz 4 in Canvas, even though I had it completed in Wiley Plus. So you should have got an announcement today that quiz 4 is now open for you to work on. Quiz 4 is a cumulative review of 255 and 256. So there's, I think, about 45 or 50 questions where there's essentially 2 problems from each chapter we've looked at over the past year. So expect no more than 2 problems per chapter. A lot of them are multiple choice, so you just click that radio button. There's some drawing, but I would say go ahead and start working on those as well. So let's apply this logic. Say that you're given the following compound. We're starting with this compound, the monosubstituted benzene ring. We're treating it under these conditions. So remember, these are nitration conditions. Nitric acid, sulfuric acid. What we need to predict is what the product of this is. So maybe in your chat box, so that we have some guidance. Is the existing substituent either A, an electron donating group, or B, electron withdrawing group? So we have a couple people answering there saying A. So A is the correct answer, and it's electron donating group. Let me just show you a resonance form of why that is. So you have a heteroatom bearing a lone pair. That lone pair of electrons can be pushed into the ring through resonance. So there's a resonance form. And again, the reason it's important to understand this, what this really means, electron donating group. These electrons are pumped into the ring. The ring now has more electron density than it started with. So this substituent makes the ring react faster than benzene. Notice the location of this lone pair here. Just going to go ahead and show you the resonance forms for this. So look at this lone pair relative to the substituent. This is ortho. Now here, 1, 2, 3, 4. This is para. We draw that last resonance form. So now it's ortho again. So these resonance forms explain why an electron donating group is an ortho-para director. So we've classified the substituent electron donating. We know these conditions are nitration. So we're going to get a product distribution. So there's the para product. This will be the major. The minor product will have the substitution taking place ortho. The reason that this is the minor product, you have these substituents right next to each other, and we saw from conformational analysis, this has a volume, this has a volume, so you get this interaction, this steric clash between them. So the major product will typically be para greater than ortho, because you have this, they're not clashing into one another. Any questions on this one? So let's go ahead and look at another one. So the same logic applies in more complicated cases. So now we're starting with a di-substituted benzene. We have an acid functionality. We have a halogen functionality. We're treating it with nitric acid and sulfuric acid. So this is going to be nitration again. So we need to predict how these substituents direct this nitration. So we're going from di-substituted to tri-substituted. So a way to do this, first let's categorize the acid functionality. And you can just type EDG or EWG into the chat box. Is the acid electron donating group or electron withdrawing group? So if it's electron donating, EDG, electron withdrawing, EWG. So it's an electron withdrawing group. So in my red marker, because it reacts slower than benzene, I want to show that like sort of like the rate it reacts slower. So as an electron withdrawing group, it's going to direct the nitration meta. So 1, 2, 3. So I'm showing in red how that directs. The halogens, again, were a mixed bag. They're electron withdrawing through induction, but electron donating through resonance. So overall, we classify them as electron donating groups. So now here's the sort of rub. An electron donating group donates orthopara. The para position is blocked, so nothing can happen there because there's already substituent. Because it's electron donating, I'm going to write that in green. The ortho positions are still open, so I'm doubling those arrows up. And even though this makes the ring react slower, this makes it react faster. Overall, the arrows align with one another. It doesn't matter which ortho it goes to, or meta and related to that. If we install one of them, it's going to direct it there because the arrows line up. We'll look at cases where one substituent will dominate over another, but for this one, since they align, we're going to get the following product. So now we have a tri-substituted benzene. Any questions on this one? Let me go ahead and erase this. The next one we'll look at, I'm going to give you this and that, and you got to tell me the order in which we run the reactions. So we're going to start with aniline. So you have to figure out the conditions and the order to run those conditions to produce the following molecule. So why don't you take, say, a minute or two to think about how we would go about doing this before I write anything else on the board. Okay, so maybe what I can do in terms of the conditions, maybe because the aniline amino group is there, maybe what I can do is write by the substituent what the conditions are to get it on there. So for bromine, remember we saw Br2, FeBr3. That will install that. Nitration we saw a couple times, HNO3, H2SO4. So that takes care of what the conditions are. Now the next thing is the order. So if I call this, say 1 and that 2, maybe in your text box you can write the correct order. Is it 2, 1 or 1, 2? Anyone else want to throw an answer up there before we go ahead and explain our way through it? So Trevor says it's always safe to bet against him. I think in this case, Trevor's actually correct. What's Ireland typing? She was typing. So the order is 1 then 2. So what you need to do a couple things. You need to recognize the conditions. How do you get it on there? Then the more important thing after that is the order in which you do it. The reason we want to go with this and then this is how we get the substituents to direct the following reactions. So let me go ahead and erase this stuff here, then we'll do the analysis. So again, we want to go 1, then 2. So we have an amino group. An amino group is an electron donating group. So it's going here, here, and here. So ortho, ortho, para. We can see from what we're trying to make, we need the nitro group in the para position. So if we do that first, if we nitrate, we said that predominantly we're going to get the para product as the major due to steric interference. So again, for electron donating groups, para is greater than ortho. So now we have that relationship established. The amino group, we've substituted para. It's still donating to the ortho, which is free. Nitro is electron withdrawing, so it's a meta-director. Those arrows are now aligned. So they're both reinforcing each other at this position here next to the amino, so we can get the bromine specifically in that place. So if we look at doing it the other way, so this is correct. If we do it the other way, there's no magic or voodoo in these reactions. Even though your eye sees the bromine is next to this amino group. And we know that electron donating groups are ortho-para directors. Just because we want this bromine to go there, it's not going to go there if we run this first. The bromine will go here if we do bromination first. So we're going to get a 1-4 relationship instead of the 1-2 that we desire. So by doing it this way, we get the arrows to basically align with each other, reinforcing the directing group abilities of each. Even though they, in terms of the rate, this is faster, this is slower, they're still directing towards the same position. Any questions on that before we move on? So that's a very brief taste of what we're doing with knowing these reactions. I want to introduce you to a couple more reactions that are important for us. And basically what they have to do with is flipping the directing group ability of an existing substituent. So, sort of where this is headed, we know that nitration will get NO2 onto the ring, but we have not seen how we get like NH2. Again, these things, NO2 versus NH2, they direct differently. We know how to get this on, but we don't know how to get that on. So what we're going to do over the next 15, 30 minutes or so is look at some more reactions to expand our toolkit here of how we get substituents on and how we can manipulate the directing group ability. So I'm going to call this functional group transformation, FGT. And we're going to see that once we have a substituent on the ring, if it directs a certain way, we can run another reaction that transforms it into a group that will direct it the opposite way. So say we're starting with benzene. We're going to do a Friedel-Crafts alkylation, say with methyl chloride. And iron trichloride. Note this is a primary or methyl halide. This is the only one you can use that will not rearrange. That was a big topic last time we met. We're substituting H for methyl. This is called toluene. Toluene, this carbon again, the benzylic carbon of toluene, it does not have a lone pair of electrons, but what alkyl groups can do is donate by induction. So that's through the bond. This is more reactive than benzene itself. So in essence, alkyl groups are ortho-para directors. Again, Friedel-Crafts is the method which we get carbon onto the ring. This next reaction we're going to show, notice these ortho-para locations. We're going to change this carbon's oxidation state so that we flip it to be an electron withdrawing group and therefore a meta-director. So the conditions to do that are potassium permanganate, sodium hydroxide, and heat. Then in a workup step, dilute acid. So what's that going to do is oxidize this carbon from oxidation state 0 to 3. So now it's a benzoic acid. And so the acid functionality is a meta-director. And just to clarify, I'm showing these arrows in red to note that they react slower than benzene itself. So electron withdrawing groups react slower than benzene, and they direct towards the meta position. The electron donating groups, either through resonance or induction, react faster than benzene, so I've shown them in green in their ortho-para. So this is a strategy we can use using Friedel-Crafts to get carbon onto the ring. In this form, the carbon is electron donation through induction, so it's ortho-para. If we oxidize it to the acid, we're then flipping the reactivity, so now it's a meta-director. Any questions on that? Okay, so before I erase this board, let me just make an announcement. Like I said, the quiz 4 is now open. You should be able to work on that. Homeworks 9, 10, exam 4 bonus is open as well. So you should be working on those things a little bit each day to take care of them. Your exam 4, again, will be on this material. So that's a couple chapters from your book. It will be 30 problems. It will open, I believe, May 6th and close May 7th. Similar format once you start it. You will have, 75 minutes to complete it. So 30 problems, 75 minutes. The final exam is going to be the same format, except it's going to be cumulative. It will resemble more like quiz 4 for the most part. Where I'm probably going to pick 2 problems from each chapter, 2 or 3. And then you'll get whatever time the university is allowing you for the final exams. But it will be open for 24 hours, and you have like 2 or 2.5 hours to complete it. So let me go ahead and erase this. So this is a functional group transformation that flips the reactivity. We're going to look at another one of these. And then we'll sort of get a little bit deeper into the reactions of the amino group. Okay, so we're going to do another functional group transformation, except this time we're going to look at nitrogen. So here we know we're starting with benzene. We know that these are nitration conditions, which will substitute this for NO2. We know that the nitro group is electron withdrawing, so it's a meta-director. So what really is a nitro group? So if you're let me draw out NO2. So that's the nitro group. Nitrogen is bonded to oxygen in a couple different ways. So the nitrogen is oxidized. The plus charge is what is causing the ring to be electron deficient. So in a functional group transformation of this, if we treat that with tin dichloride in ethanol, so that's one set of conditions, or we can use hydrogen gas with palladium metal on carbon in ethanol. Or, so these are three different sets of conditions. You would choose one of the three: iron metal, hydrochloric acid, and then sodium hydroxide. Any one of these three conditions reduces the oxidation state. So we're going from nitrobenzene to aminobenzene or aniline. And again, that's an ortho-para-director. So the functional group transformation, after we get the nitro in, we can reduce it to get the amino group in and flip the reactivity. Any questions on either of those functional group transformations? So maybe before I start the next thing, I can pull some problems from the book. We can do problems for about 10-15 minutes. Then we'll continue on with some more lecture stuff. I'm going to go ahead and erase this. We'll do some problems. And then with this, we know how to get nitrogen onto the ring. This is going to be crucial for us moving forward. Let's just take a step back and do some review problems. Chapter 18, number 55. So it says, in each case, identify the most likely position at which monobromination would occur. So what's the challenge with this problem? You have two benzene rings, and essentially it's saying you're treating with, you have two rings, you're treating with one equivalent of bromine. So which ring will be brominated? So let me say, if this is ring A and this is ring B, in the chat box type A or B, which one gets the bromine? We'll see what you respond, and then we'll talk about some logic. A couple people have said B. So B is the correct answer. So let's think about why that is. When you have these, this is what I said, what I meant before when I said about one molecule with different types of benzenes. So if you're looking at, let's just cover this up now. We're covering that second one up. If we're just looking at this, again, we're not considering that ring. This substituent is an electron withdrawing substituent. Electron withdrawing, I'm showing in red where it directs, and I'm using red because it's electron withdrawing. Now if we cover up this part of the molecule, that looks like toluene, just a methyl group. We know that that's an electron donating group, so it's orthopara. So this ring reacts faster than this ring because of that substituent. And now since you've done that, we know that electron donating groups are orthopara, electron withdrawing groups are meta. We know that it's going to be, and the preferred substitution is going to be at the para position. So this is one of the reasons why I finish off Organic 2 with aromatic chemistry, because by now hopefully you can see that the decision-making processes to answering the questions are a little bit more straightforward because they're rooted in sort of these flow charts or algorithms you can evaluate. So let's look at another one. Similar to this, again, it's going to be monobromination, but the molecule itself will change. So this would be 1855B. This is actually so if we call this ring A, this ring B, in your chat box, which ring is going to be monobrominated? So again, yeah, this will be B. And how we think about that is we have a benzene ring with a carbonyl. The carbonyl, if we're covering this up, that's electron withdrawing. We have this ring, if we cover that up, the nitrogen directly bonded to the ring is electron donating. So the major product is going to get brominated there. So the electron donating groups always win over electron withdrawing. And the para always wins over the ortho. Any questions on this one before we move on? So I think what we'll do, that went a little quicker than I thought. We'll get into the next sort of suite of reactions we need to learn so that we can really have a big picture idea of how to make basically any substituted aromatic ring. So if you recall from last week, we know how to get halogens on the ring. We know how to get carbon on the ring, sulfur, nitrogen. We did not see of the halogens fluorine or iodine. We didn't have conditions to do that. And we also did not see conditions to get oxygen directly onto the ring. So this next set of reactions falls under this category called diazotization. And it's basically we're taking aniline, so aminobenzene, we're going to derivatize that, and then we're going to see we can get these different atoms directly bonded to where that original nitrogen was. So let me just put up what this means. So we know how to arrive at aminobenzene. We do a nitration of benzene, then we do a reduction, that gets us the aminobenzene. We can take this typically we're using sodium nitrite. So pay attention to the end here, nitrite, NO2. Nitrate is NO3. Sodium nitrite, excess hydrochloric acid. This will generate HNO2, which is called nitrous acid. I'll show you the mechanism how this works, but now I'm just giving you the conditions. The nitrous acid transforms this into the following intermediate. Which is called an arene, A-R-E-N-E, arene. Diazonium salt. It's a salt because the nitrogen's plus and the chlorine's negative. Essentially what it is, it's an oxidation of this nitrogen. So now you have a nitrogen bonded to another nitrogen, so N2, overall a plus charge. Maybe let me just draw that out so you can see what it looks like. So the plus charge is on that nitrogen. And really, these things are very reactive. Diazonium salts are very reactive because what this wants to do, it wants to substitute an atom here and then basically eliminate or substitute off nitrogen gas. So when you actually run these reactions, you will see gas evolved from the reaction flask. And that's the N2 gas leaving. So as I look at my notes, I see I do have quite a bit written for the mechanism of this. I don't know if it's really worth it showing you how this reacts with that to form this. These are the conditions you need, though. An amino group plus nitrous acid to give you that. So really, I think the time is better spent showing how this can be transformed to do substitutions and get these other elements in the molecule. So I think that's what we'll probably do for the rest of today is I'll show you that. And then when we continue, I believe we have we have Wednesday, and then next Monday is our last 2 lectures. Your exam 4 is next Wednesday, and then your final exam is the following Monday after that. So what we'll do is I'll show you these transformations. Wednesday we'll go over multi-substituted benzene syntheses. We'll work a couple different problems for that. Next Monday, we'll finish up or maybe review, depending on how the time goes. So I'm going to go ahead and erase this and show you how this thing can be transformed to get these other substituents onto the ring. I'm going to start plunk in the middle here. So we've gone ahead and we've made our diazonium. So I'm going to show you a manifold over here. So each of these are separate reactions, starting with this. We can go this way, second, third, or fourth. So they're separate things. They're not something you would all do at once. These are just going to be conditions to get the different halogens in. So if we want to get fluorine, if we want to make chlorobenzene, we would use this compound here, HBF4 in heat. So we're treating the diazonium salt with tetrafluoroboric acid and heat. And that's substituting the N2 for the F. And really what these are nucleophilic substitutions. The F will attack this carbon. You'll get a displacement, like I said. The nitrogen will leave as nitrogen gas, it bubbles out. That's how we can get fluorine into the molecule. Even though we've already seen how to get chlorine and bromine, we can use copper 1 chloride to get chlorine. We can use copper 1 bromide to get bromine. And the reason we would want to do something like this is because you're not always able to use like Cl2 or Br2 if you have other functionalities that those molecules will react with. So the last one, we can get iodine finally into the molecule using potassium iodide. So there's our halogen manifold, starting with the diazonium. So over here, I want to show you 3 other reactions. The first one, how do we get oxygen into the molecule? We're going to use copper 2 oxide with water. The oxygen is coming from the copper oxide. This is just to solubilize it. That's going to transform N2 into OH, so we can get phenol. So again, we're displacing the N2. We get the OH group in, we get phenol. We can use another copper salt, copper cyanide. That gets us the nitrile group. So copper, you see this in a couple different places. Copper is pretty special for these because it's a transition metal. It allows for basically the energy of activation to be lowered for doing this displacement. So the last one that I want to show you on this manifold, H3PO2. This would be running water as well. This is called hypophosphorous acid. Phosphoric acid is H3PO4. Notice the oxidation state is lower, so hypophosphorous acid. And what this is going to do, one of those hydrogens is going to replace that N2 group. This reaction has a name, this last one. It's called deamination. So you're removing the N2, you're essentially reducing the oxidation state of that carbon and substituting it for H. You might be wondering, why would I want to do that? if it took me 2 reactions, no, 3 reactions to get to here. So if I started with benzene, I did the nitration to get the nitrobenzene, I did the reduction to get to aniline, and then I did the diazotization to get to here. Why would I want to remove that nitrogen and replace it with hydrogen? This really allows us to take advantage of the reactivity of the nitrogen in the different oxidation states. And then once we do that, we can completely remove it. So it's acting as a director and also a blocking group. So in the last couple minutes here, let's look at the following. Let's look at a problem where we need to deploy this strategy. Any questions before we move on from this whiteboard? So let's consider the following synthesis. We're starting with toluene. We have the methyl group in place. So if we were actually in class right now, you guys would get into groups and take time to consider this. So I'm going to give you some prompts that we'll think about and we'll work our way through it. We're starting with toluene, and we're ending up with this compound here, which would be, say, 3-methyl, 1, 2, 3, 3-methyl aniline, or 3-methyl aminobenzene, however you want to name it, beta methyl aniline. So we're starting with this, and we're ending with that. So what are the challenges here? We know how to get nitrogen onto a ring. We do a nitration, then we do a reduction. What are we starting with? Is this electron donating or electron withdrawing? So it's an electron donating group, right? So with my green marker, I've pointed that out. So again, I know it's late in our learning of organic chemistry, but this is where metacognition comes into play. What this is telling you, this thing is going to direct ortho, para, with para being the major. But look what's there. There's an H there. You can't just go do a nitration reaction and expect that this somehow is going to direct to put a nitrogen there and then we can reduce it. That ain't going to happen. So what this is telling us, this is going to take quite a few number of steps to do this. So if we know that this reactivity is orthopara, we have to take advantage of that. So the first thing we can do is a nitration. And again, this is a strategy. I don't expect you to fully, say, come up with this on the first go. You have to do a lot of these to really understand it. So NO2. We get the para product over the over the ortho. Now we sort of do the same analysis of each substituent here. This is ortho para. The para was blocked. This is electron withdrawing. It's a meta director. That doesn't do us any good. The next substitution is going to happen in a 1-2 relationship to the methyl. But we see there's hydrogens there. We need it 1-3. So what can we do next? We can reduce that. We can use iron, metal, HCl. Then a basic workup with sodium hydroxide. So now we have two electron donating groups. So this is through induction, this one's through resonance, so I'm going to make those arrows bigger. So even though they're in different spots, because this one is happening through resonance, it has a greater effect. So the next substitution is going to happen relative to that amino group. So now what we can do, we know that this substitution has to be nitrogen, and the only way we can do that is with nitration. So we do another nitration, HNO3, H2SO4. I know we're about out of time, but just let me have another minute or two. So now look at these. You have nitrogen amino, nitrogen nitro. They're at different oxidation states. And we've seen reactions that will affect them differently. So how do we get from this to that and this to that? Well, basically at this point, we want to get rid of this amino group because we need to transform that one into an amino group. So in our series of steps here, the first thing we're going to do is the diazotization with HNO2. Then we're going to treat with H3PO2. So that's basically going to transform this amino group into the hydrogen. Then we need to reduce this into that amino group. So the third step, we can use tin, dichloride, and ethanol, which will reduce that to the amine. So then you can see how, even though we didn't start with something that directed properly, we installed the nitro group, reduced it, which then helps us put it in where we needed it, and then we got rid of it. So that's called the blocking group strategy. I know that was a bit much to unpack at the end there, but we'll spend the next lecture going over a lot of these so you can see how to sequence these reactions to get the relationships right. So if you have any questions, again, we're out of time, so shoot me an email. We'll see you again on Wednesday at 1. In the meantime, try to work on those Wiley Plus assignments. Other than that, I'm going to go ahead and shut the live stream off now, let you guys go. So we'll see you Wednesday. Take care.